Sixth grade science students, today we're doing a demonstration, or a few demonstrations, but we'll start with this one, on heat expansion and contraction. We have this apparatus that I put a picture of on OneNote, and it is called a ball and a ring. And so, Kara, what do you notice about the ball and the ring?
They're both metal.
Right?
Probably brass.
Okay.
And the ball fits perfectly in the ring.
Okay, very good. So that's pretty cool. And what we're going to do today is we're going to do some things. We're going to take this ball, which is made of metal, and we're going to heat it with this candle. And I want you to think about what's happening right now with this ball over a flame. Cameron, any ideas?
Heat energy is transferring from the flame to the ball.
That's right. Heat is being transferred from the flame to the ball. And there's actually 3 kinds of heat transfer that my students have been learning about. I'm putting that out by accident. Cameron, do you know the 3 types of heat transfer?
Convection, and radiation.
Right. So radiation is occurring because the light and heat from the flame. And conduction is also occurring because it's actually touching, and that's what conduction means. So a metal, like this brass, is a really good conductor of heat. And I can actually feel it. I need to move my hand down to the handle, and I want to get this nice and hot, so I'm going to do this. Kara, why do you think the handle is a different material?
So that, because metal touching metal makes it, makes the heat from the ball travel down from the spoke to the handle, and if the handle was metal, it would get really hot.
Right. What's it called, Cameron? Do you know when a material does not conduct heat well, like the handle?
Insulator?
Yeah, it's an insulator, a thermal insulator. It's protecting my hand. So let's think about the ball and the ring now. I'm really heating up this ball of metal. We know it's going to get hot because it's a conductor. But what do you think is going to happen when I try to put the ball through the ring?
I think it'll be smaller than before, because before it fit perfectly inside the ring.
Okay, so you think which will be smaller? We didn't do anything to the ring.
The ball.
You think the ball will be smaller and it'll go right in easier? Yeah?
I don't think the ball will fit.
You think the ball's not going to fit?
I don't know why. I don't think it would actually grow, but it's gaining energy. It's not losing anything.
Okay. All right. So we're going to try it in a minute. Cameron, can you pass that ring to Kara carefully, please? And then we're going to try it really fast while the ball is still hot. Okay? All right. You ready?
Yeah.
Okay. What do you notice? Ooh, it's what? It fits, but we really had to jam it, didn't we?
Yeah.
All right, so what if we then really make a temperature difference? I want you to think why that happened. But now I'm going to get the ball even hotter, and I'm going to get the ring in ice water. So, cameraman, Caitlin, if you can zoom in on that ring in ice water.
Now I bet it's really
Now,
not
what do you
gonna
think? So wait, let me hear your prediction, Kara.
Now I bet it's really not going to fit, because I feel like when things get colder, they shrink, and when things get hot, they get bigger.
Can you repeat that, please?
I feel like when things get cold, they get smaller, and when things get hot, they get bigger.
So, Cameron, do you remember what I said that this demonstration was called? Thermal?
Conductivity?
No,
I wasn't listening to you.
Thermal expansion
Oh.
and contraction. So what do those words mean?
Getting bigger and getting smaller.
Exactly. So Kara's right on the right track. When things are heated, their molecules move apart and they actually get a little bit bigger. And it's hard to see. It's not visible in most cases, but they actually get bigger. And when things are cool, their molecules slow down. They get closer together. Think about if you were in a big giant room and you were freezing cold. You'd want to get huddled together with your friends and get close to get warm, right? But think if you were in a big gym and everybody was hot and stinky. Wouldn't you want to move away from each other?
Yeah.
That's kind of what molecules do. So let's make a prediction. What do we think is going to happen now when we try to put the ball in
The ball's
ring?
not going to fit into
All right,
the
we're
ring.
going to try it. Cameron's going to be the one to try it this time. So go ahead. And right now, by the way, the ring, what's happening, put the ring back in for just a second. In the ring, the heat is moving from the ring to the ice water. from the ring to the ice water. Cold can't really move, it's heat that moves. So heat is moving from the ring to the ice water, making the ice water a little warmer and the ring cold. And in theory, supposedly, the ring should get a little tiny bit smaller because the molecules are cold, they move together, they huddle together, and they get close to each other, and it should contract. And this ball should be getting a little bit bigger, a little bit more expansive. The molecules should move away from each other. So let's go ahead and try it. Ready? Okay. Good.
It's fitting, but you really have
Really, right? So can you tell the slight differences in size from the contraction? Now what if we go ahead and do the opposite? And if we put this in the ice water and heat the ring, now we're backward.
It should fit because then the ball will get smaller and the ring will get bigger.
Right, so this way now the ring is expanding.
But it shouldn't fit perfectly like before because
I think it will fit perfectly.
Yeah, I think we're going to reverse the original, right? And it should fit more easily again.
yeah.
So the ring is going to be expanded because the molecules are hot, they're moving away from each other. And the ball is going to contract now because when it's cold, the molecules move closer to each other. And it should fit much more easily. So I think we've gotten enough expansion and contraction. All right, let's go ahead and try it.
Oh, see? It doesn't even fit really perfectly.
Yeah, it fits so easily, right? So that is thermal expansion and contraction. I hope you enjoyed this demonstration, boys and girls. More to come. Girls, another demonstration on heat. And here we have Cameron again, my 16-year-old daughter, and Kara, my almost 9-year-old daughter. And I have 2 bowls of water. So cameraman Caitlin, can you move on in? I have a bowl of ice water, really cold, and a bowl of hot water that I put in the microwave. And I have 2 of the same water bottles, and on these water bottles I put these balloons, tiny little balloons, pink for the one that's going in the cold, and green for the one that's going in the hot. And I want you to think these water bottles are filled with air, even though you can't see it. And I want you to think what is going to happen to the air in the water bottles as I place these 2 balloons in cold water and hot water. So let's take a look.
Oh, that one's getting bigger.
So, I want you to think about what the difference between the 2 balloons is. I want you to think about what's happening inside each one of these water bottles. And I want you to think about why that is happening. So, Kara, what do you notice happening already?
Okay, so this balloon is filling up with air, and this balloon is basically doing nothing.
Okay, very good. So that's a good qualitative data observation. Qualitative data is data with words and pictures. Cameron, any idea if you could explain what is happening in either one of these bottles?
Well, I learned in school that there's these things called gas laws, and when temperature increases, volume also increases. So since it's the temperature of the water bottle and the gas inside the water bottle is increasing, the molecules are moving faster, making the volume increase.
Very good. So in other words, when things get hotter, they expand, right? It's called thermal expansion. And when things get colder, gases like air, they contract. So they actually get smaller. Its volume, and that's a math word in 6th grade math, is getting smaller. But the air inside the water bottle, in the hot, is actually taking up more space, has more volume as the temperature increases, and since it's taking up more space, some of it's moving up into the balloon. Hi boys and girls, time for another demonstration on heat. So here we have a tea bag, and I'm going to open it up and just dump out the tea. Seems kind of wasteful, but all in the good name of science. So I'm gonna just open this up. It's just a regular tea bag. It's a little bigger than usual because this is a tea bag that's for iced tea, so it's a bigger one. And you can see, I don't know if you knew this, but a tea bag's just really made of filter paper with tea leaves in it, and it makes a cylinder. And I'm going to dump this out here on the table. And I'm going to place this like this. So this is a cylinder of just light paper. And I'm really going to light it on fire and it's going to get hot. And I want you to think about what you think is going to happen. So right now, just think and predict what you think will happen. So Cameron, what do you think will happen when I light this on fire?
Well, first of all, it's probably going to catch on fire and burn.
It
But
is
also,
paper.
we've been talking about thermal expansion, so it's something's probably going to be bigger.
Okay.
It's
How about you?
probably going to fly up because, like, you know, hot air balloons. Some hot air balloons have like fire or like hot.
That's
things
a
at the
really,
bottom.
really good prediction. Somebody may have been watching some videos on heat expansion and convection and conduction. That's okay. Let's try it. So definitely you were right. It's on fire.
And
It's
it's
burning
really
down. Now
fast.
hot. It's getting hotter and hotter. Now hot air is getting to the bottom of it. And let's see what's going to happen.
Whoa.
Okay, so as it burned, I want you to burn yourself. As it burned, nothing seemed to be happening at first, right? It was burning, 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 and then what happened at the very end?
It flew up
Yeah, why do you
like
think
a
it would do
hot
that?
air balloon
Right,
because
the air at the bottom got heated up. That hot air under the tea bag wanted to rise, and so just like a hot air balloon, that light filter paper tea bag rose up. So that was really cool. I hope you liked that demonstration. Hi boys and girls, we're continuing with our demonstrations on heat. And this is about heat expansion. And so I have a balloon here. It's filled with air, just a regular balloon that you buy at the store. And what do you think is going to happen if I hold this over our candle and get it hot?
it might pop because things get bigger when they overheat.
Yeah, what do you
And if
think,
balloons
Cameron?
get too big, they
I agree with her because I think the volume will increase when the temperature increases, and the volume of the gas molecules will increase, and they'll get so big that they won't be able to fit in the space.
All right, so let's take a look at it. Stand back. Ooh, that happened in about how long?
0.7.
Yeah, not even a second, right? All right, now I have this balloon, and let's see what happens with this balloon. Okay? Yeah, do you see the bottom? I put a
There's
little
a
water
little
in it.
water.
See that? Do you think that'll affect it at all?
Yeah.
All right, let's take a look. Still popped. Did it take a little longer, do you feel like?
Yeah,
Why do you feel like it would take a little longer?
because water's a conductor.
Oh, good, because water actually absorbs some of the heat. And even though both of them popped because the air had nowhere to go, it got bigger and expanded because of the heat and had nowhere to go. If you put a little water at the bottom, it absorbs some of that heat and takes a little longer for the air to expand. Hope you enjoyed that demonstration. Hi boys and girls, welcome to another demonstration on heat and heat transfer, convection, conduction, and radiation, and heat expansion and heat contraction. So this is another demonstration. We have a spiral of paper here. We just cut around like a circle, like a snake. Cameron made it. Good job, Cameron. And we have it balanced on a toothpick, or we didn't have a toothpick, so we used a fancy drink umbrella toothpick. And is it moving right now, Kara?
No,
No.
it's very still.
Yeah, we don't really have our ceiling fan on or our windows open, so we don't have a lot of air movement in our house. And so what I'm going to do in just a minute is I'm going to take this lighter and I'm going to just light the lighter and heat under the spiral. I'm not going to light it on fire. I'm just going to heat it under. And let's make some predictions. Kara, what do you think will happen?
I think it might spin.
Okay, might. Cameron, any suggestions?
I agree with her, but I think it's because when you heat up under here, hot air likes to rise up like in an air balloon, so it'll cause this to want to like start spinning around to move.
Right, so let's try it, okay? So I'm just going to light the lighter and put it right under the spiral. As you can see, as the air under our spiral gets hot, that hot air wants to rise. And when the air rises, it creates some heat.
Thank you for watching our 5 demonstrations of heat. I hope you enjoyed them as much as I did. Bye!